Hello and welcome to the vodcast 4.4b, part of Wave Behaviour, part of Waves, looking at total internal reflection. So we're getting towards the end of this quite large unit now. We're going to be looking today at the critical angle and total internal reflection. We'll also be sort of carrying on with Snell's law because that's integral to the whole process. And we'll be looking at solving problems involving critical angle and total internal reflection as well. So just to review from the last session, this is Snell's law. We're looking at light rate. Well, technically we're looking at refraction, and refraction is any wave where it has a situation where it changes speed. However, I should make it clear that for this topic, this particular topic, total internal reflection, critical angle, we're really just looking at electromagnetic radiation, which technically we could be looking at infrared or microwaves, but even within that, we're pretty much going to be looking just at light, visible light. One of the things that is dependent on refraction that isn't specifically mentioned in the guide, but is really needed to help understand what we mean when we're talking about refraction, and also some of the properties that light exhibits, is dispersion. So dispersion is the spreading apart, dispersing, to spread apart light rays. As I hope you know, white light is a mixture of different wavelengths, and those different wavelengths correspond to different colours. As we've looked at before, the rods, the cones in your eyes, in your retina, are sensitive to different wavelengths across different wavelength bands. By different wavelengths activating some or all of your rods or cones in different amounts, then they give rise to your colour perception. Problems with this, by the way, give rise to conditions such as colour blindness. So here we have, in this picture, a white light beam entering a prism. Then it is being dispersed into the pattern, the sort of rainbow or spectrum pattern that you can see there. So this kind of process where a prism disperses the light happens due to refraction. That white light enters in, it occurs, it bends towards the normal as it enters. Now, previously the amount it's bent by we've looked at as purely being defined by Snell's law. However, what you haven't learnt is that that is wavelength dependent, because the velocity, apart from in a vacuum, everything travels through a vacuum at the same velocity, or light does. In any other medium, the velocity of the light in that medium depends on the wavelength of the light. And because it depends on the wavelength of the light, it means that it's bent by a slightly different amount. So as soon as it enters the prism, it starts to be spread apart because different amounts for different colours, and then the geometry of a prism is such that when it bends away from a normal and exiting, it's kind of bending overall in the same direction again, which just accentuates that process. It spreads it out even more, so you get a greater dispersion of light. So any interface boundary between two transparent media can give rise to dispersion of light. However, it's most effective when you have this sort of geometry that reinforces and amplifies that dispersion. And that leads you to a spectrum, and the thing to remember, if it's one of those things that's probably a good idea to remember, is that blue bends best. In other words, blue rays are slowed the most and therefore experience greater refraction than red. Total internal reflection, which is what's demonstrated in this picture, is a different process. Here you have a laser beam shining into a container of water, and it goes kind of straight through the plastic or glass because it's very thin, and so you don't notice much refraction. It happens, but you don't notice it very much. But you'll notice that that laser beam then travels through the water, but when it gets to the surface, it does not refract. Instead, it just reflects off the surface of the water. Now, the surface of the water it's water, it's translucent. I mean, as you can see looking at this picture. So why does it reflect instead of refracting? Well, that's down to the mathematics and the physics of the situation. When refraction happens from a slow medium to a fast medium, such as leaving glass into air or vacuum, or leaving water, or any kind of situation where you're going from fast to slow, the light bends away from the normal. But logically that means that there is a critical angle at which that light ray would be bent through 90 degrees from the normal, which in other words is keeping it inside the material. The moment that happens, you get this total internal reflection process occurring. And we can do the mathematics of this, theta 1, theta 2. If we say that theta 2 is 90 degrees, then sine 90 degrees is 1. So we can replace that with 1 there. Theta 1 is the critical angle, theta c. And we have n1 and n2, which is the refractive index of the two media. If we assume it's going into a vacuum or into air, which is almost the same, again, we can put another 1 there. Rearrange this equation. Sine theta of the critical angle equals 1 over the refractive index of the slower material, or critical angle is sine to the minus 1 over the refractive index of the more optically dense, as we sometimes call it, or greater optical depth material, the one in which it's going slower. Some refractive index of some common materials there are water 1.33, 1.50, 2.42. Just to go back to what we were saying about dispersion, by the way, when we say refractive index, we do actually mean the average refractive index across what we're interested in, across visible light. Different wavelengths, as we said, will have a slightly different refractive index. And these lead to these values of the critical angle. Okay, so for water and glass, if that critical angle, looking at the picture there, goes above 41 or 48 degrees, depending on what you've got, you'll have total internal reflection. The most highest refractive index of just about any material, particularly any natural material, is diamond. Light slows down an awful lot when it goes through diamond, which leads to a critical angle of only 24.4 degrees. This, combined with the dispersion that we've been looking at, is what makes diamonds particularly beautiful and sparkly. If you shine white light on them, they will tend to trap that white light. It will tend to bounce around inside the diamond, and then eventually leave at different angles through the cutting and through the dispersion, leading to the sort of spectrum and sparkly nature of diamonds. One more point to note is that when there is refraction, there is also reflection. Oh, there's meant to be an image there. Sorry, I don't know why that didn't work. But if you have a situation, going back to it, a situation like this, for example, where the white light is hitting the prism and then is being dispersed out here, this is refraction. There will also be reflection. If you were stood here, some of this white light would be bouncing off and you would see a reflected rate there. So reflection, wherever you get refraction, you get reflection. Not obviously the other way around. You can have reflection without refraction. Total internal reflection involves no refraction. But whenever you have refraction, you do have reflection, both inside and outside. So when it refracts out of the material, when it refracts here, there will also be some reflection inside the surface there. Moving onwards. So just to look a little bit more at rainbows, because they're a good application of both of these principles. Here is a nice photograph by Ken Rockwell, who's a noted photographer and reviewer of photographic products. And here you can see the rainbow. Notice the perspective of the person taking the photograph. Okay, the sun is directly behind them at this point. So sunlight is coming over their shoulders, so to speak, from behind them. And then it's hitting the water, the rain, and it's creating this pattern. So you can see here a clear rainbow, blue on the inside, red on the outside. And this is one of those rare occasions where there's particularly strong light, and that's strong enough to make visible the second outermost rainbow, which, by the way, it's not so easy to see, but has colours reversed with blue on the outside and red on the inside. Let's explain that. Well, we can explain that using this diagram here. Instant white light, sunlight comes in, it hits the water droplet. Now, water droplets, by the way, are always spherical. Surface tension holds them into a sphere. That cartoon water droplet you might have seen with like a pointy end, that doesn't exist in reality. So water enters, and as it enters this surface here, it refracts, bends towards normal, and starts to disperse. It gets to the bottom, the backside, so to speak, of the water droplet. And here it's greater than the critical angle for water in this particular case, so therefore it totally internally reflects. It comes back out. Now it's not within the critical angle, so it refracts out, and you have dispersed light, which, because it's done this TIR, this total internal reflection at the back, is now coming back in the direction it first came from. So that's why you see that rainbow coming back towards you. The light from the sun, the dispersed light from the sun, is now coming back towards you. And that second outermost rainbow, well, as we said earlier, there is always some reflection. So if the light is strong enough, then you'll have some reflection, which will come off here. It will totally internally refract again a couple of times, and then it comes out at a different angle, which is why it actually comes out down here, I think. It's a different angle, which is why you see a much fainter outermost rainbow with the colours reversed. Other applications of total internal reflection include optical fibres. So here's a somewhat frivolous application of optical fibres. There are some more serious applications as well. In optical fibres, you have two parts of transparent material, two transparent flexible glasses, a core and then an outer cladding, which have slightly different refractive indexes. Because they have slightly different refractive indexes, they have very large critical angles. So the light ray will, unless you really bend over that optical fibre to make a very tight corner, it will always be greater than the critical angle, and therefore will always remain within the cladding. And this is such transparent glass compared to normal window glass. You could make window glass kilometres thick, and it wouldn't be as transparent as this special flexible transparent glass. Then those light rays can carry on for hundreds of meters, kilometers out the other end, which leads to their uses, which is that compared to, and one of the serious uses of optical fibers is sort of communications, where instead of electrical signals traveling down wires, you can use flashing lights instead. You have high bandwidth because you can combine different wavelengths and different frequencies in a clever way to make use of multiple signals. It's relatively cheap, surprisingly so. It's thin and small compared to the amount of copper or other metal that would be needed to have the same bandwidth. It has low signal degradation. The signal, as long as it's strong enough, is much more clarity. It's less prone to interference from other sources, from radio waves creating electric currents in a wire. And it's very durable in one way, which is that it will, once it's laid down and it's there, as long as it's not disturbed, it will last a long time. It doesn't rust in the same way that some metals can. However, in other ways, it is more fragile. You cannot really twist it and bend it as much as you could with metal wire, particularly sheathed metal wire. And although it is able to go for reasonable distances, it can't go. The signal cannot go for as long as maybe in a metal wire, unless there is sort of a reboost and amplification where it receives light and then boosts it, and you have another light source that repeats the pattern. So pros and cons. Another use of optical fibres is in endoscopy. So endoscopy is the medical process where, in order to be able to sort of see inside the body, an endoscope which uses optical fibres bounces the light, a light source down, and then reflects, and then along another channel the reflected light comes back up, and a camera is used in order to identify what can be seen. Okay, so we've reviewed Snell's law, we've looked and defined at critical angle, we've looked and defined total internal reflection, and you'll be able to, we've given you some situations and solved a simple problem calculating a critical angle. I do recommend doing a lot more practice involving these sorts of problems. Thank you very much.